Welcome to our discussion on derivatives of trigonometric functions. You are going to see trigonometric functions all over the place. They're all over the calc sequence, they're all over the physics sequences, they show up in biology and chemistry and other natural sciences. So it is a good idea to be moderately familiar with all of the trig functions and then the derivatives of the trig functions. Now, most of you probably only care about what those derivatives are and not exactly seeing proofs of why they are what they are. For the very choice few of you that are actually moving on to higher order math classes, you'll want to pay attention to the details in this video of how we're going to prove the actual derivatives of sine and some of the others. But for most of you, you can kind of fast forward to that and just deal with the actual fruit of the labor and knowing what those derivatives are. Okay, so let's remember a little bit about the sine function. When we're dealing with taking derivatives and stuff, it's very important to realize that we're always going to be listing the angle in radian measurements. Okay, so it's always going to be the idea of pi over something, 2 pi, things in terms of pi rather than in terms of degrees. And then of course it's a good thing to realize that all of the trig functions are continuous at every number in their domains. Even things like tangent and cotangent, which do have points of discontinuity, those points have been removed from their domain and the functions are actually continuous at every number that's in their domain. Okay, if we sketch the graph of sine of x and then just start looking at the slopes of that graph, so basically looking at the slopes of the tangent line along that graph and then plotting those points, right? So for instance, if you look at this first one here, that's a good old horizontal slope, and that's why we have the value of the derivative is 0, right? Here's something that looks like about a -1. So there we are at -1, back up to 0, and so on and so forth. Keep connecting those dots, and you can see here that this is the sine curve, and if you don't recognize it, you should. This is cosine, or it sure looks like that's the cosine curve. In fact, we will see that it is and prove that it is here shortly. Okay, so let's try and confirm the guess. It looked like it was the cosine curve when we took the derivative. So let's start with the definition. That's kind of what we always start with when we're trying to prove these things. So the derivative of the function, remember, is f of x plus h minus f of x all over h. Take the limit as h goes to 0. Now we're going to slap in sine. So it's sine of x plus h minus sine of x all over h. Now, where did all this gobbledygook come from on this next line? Right? Where did all these sines and cosines and all that junk come from? Well, that is from one of our trig identities. Sine of alpha plus beta is sine of alpha times cosine of beta plus cosine of alpha times sine of beta. That's where this comes from. So that's one of those trig identities that you should have memorized. And then we're still just subtracting, right, the sine x from the end. Okay, what are we doing here? Well, all we're doing here is kind of rearranging our terms. We took this one and brought it over here and moved the cosine term over there, and we cut it up into two fractions, right? Because everything's being divisible or divided by h, so you can break it up and have it two different fractions over h. Okay, and then the next step, all we did was factor out that sine. So there's sine times cosine h minus 1 all over h, and then over here we factored out the cosine and got sine of h over h. Now we're going to take the limit and apply it to all of this stuff. And remembering the rules of limits, limit of a product is the product of the limits, limit of a sum is the sum of the limits, right? So you're basically, it's almost like you're distributing the limit on everything. Limit of the first piece times limit of the second piece plus limit of the third piece times limit of the fourth piece. So all we're doing there is just putting the limit on each individual piece. Okay, brings us to the next step, which I've just kind of recopied what was on the previous slide, right? Just to refresh your memory, right? We were already there with the limit of sine times the limit of blah blah blah, right? So limit of sine times limit of cosine, da 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 da. Okay, this is where we were on the previous slide. Now, two of these four limits are easy to evaluate. Since x is now a constant because h is the thing that's changing. So limit as h approaches 0 of sine of x is just sine of x, right? You're basically taking the limit of a constant because in the world of h, it is a constant because it's a function in terms of x. So as h changes, right, as h gets smaller and smaller and smaller, nothing's happening to the sine of x. And similarly, this piece here is also a constant and just equals cosine. So 2 down, 2 to go. Okay. The next piece that we're going to deal with is the limit as theta goes to 0 of sine of theta over theta, and we're going to prove that that equals 1. Now you're probably thinking, where the heck did theta come from? It's still this, right? It's still the limit as h goes to 0 of sine h over h, only now we're talking about thetas instead of h's, right? So we're just putting in the symbol that's more commonly used with trig functions, theta, a measurement of an angle, rather than h, which we just think of as just kind of a number. All right, so we want to prove that this is actually true. So let's start with a picture. We're going to use this geometric picture to help us through this entire proof. So the stuff in the blue is basically a wedge of a circle. Right? So from O to A is the radius, and from O to B is the same radius. Those are both 1 because we're going to put theta in the first quadrant. So that's why we're saying we're going to assume it's between 0 and pi over 2. And the only reason why we put it in the first quadrant is to keep everything positive, so it just makes the math sit nicer in our head. And so now we're going to kind of create this theta wedge is going to be the central angle of a circle, right, with radius 1. We're basically now going back and working with the good old unit circle that you're hopefully all very familiar with. And then we're just going to start drawing some junk all over it. Okay, take a line from B straight down to OA, right, the line OA, and that's that line BC, and it's perpendicular. So we're going to create another right triangle. Now, by definition of what radian measures are, we know that arc AB is equal to theta. That's, what theta means. It's an angle measurement, but it's also a measurement of the length of the arc. Okay? So if you don't remember that, this arc here, and boy, I'm horrible at drawing, sorry, is theta, right? They're the same length. So if theta was pi over 3, then that length of that arc, if you measured it out, would be pi over 3, which is a little bit more than 1, right? 3.1415 blah 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 divided by 3, a little bit bigger than 1. Okay, we also know that the absolute value of BC, which is basically just giving us this length here on this thing, is equal to OB times sine theta. And you might not catch that, but that comes from, remember good old SOHCAHTOA? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So if we took sine of theta, this theta, it's going to equal opposite, right, which is the length of BC, over adjacent, which is the length OC. And we just put the absolute values in there just to designate that we're taking the positive number. We're taking the lengths of those sides, right, of the triangle. We're taking the absolute value length, the measurement. So by simple algebra, sorry, I'm so sorry, this is tangent, I'm an idiot. This is OB, right? You guys, I'm sure, we're all screaming at me. It's opposite over hypotenuse, dummy, and hypotenuse is 0b, not 0c. And so opposite over hypotenuse. So there's the ratio for sine. And then with simple simple algebra, long day, we're going to multiply both sides by this number. Right, so whatever this number is times sine theta equals BC. See, that's where they got this thing equal to BC. And then you're thinking, okay, well then how is that just equal to sine theta? Well, it's equal to sine theta because what's the length of OB? OB is just 1, right? So it doesn't do anything. That's why it's just equal to sine. So all of this is just showing that sine theta equals the length BC, right? Okay. Now, take a look at this diagram. The blue wedge is still the same wedge we were dealing with previously, with OB, right, and OA being the radius, and BA being the length of the arc that comes from our theta that's sitting right there. If we look at it this way, we can see very plainly that BC is less than AB is less than the arc AB. And you go, yeah, sure, I can see that, right? Where does that come from? Okay. We know that BC is less than BA because this is a right triangle and the hypotenuse is always the longest of the three sides. So there's these two. BC less than AB, right? This way. BC less than AB. And then how do we know it's less than arc AB? Well, can't you see that AB is definitely bigger? The arc AB is definitely longer than the straight line, because we know the shortest distance between 2 points is always a straight line, so the arc is bigger than AB. That's where all that comes from. Okay, so that tells us that sine theta is less than theta. And you go, well, how the heck do I know that? Well, it's by substitution. What was sine theta? Sine theta was equal to BC, right? So by substitution, this is just saying sine theta is less than AB, which is less than arc AB. But remember, the arc is also the same length as theta, right? This arc just equals theta. And that's where we get sine theta is less than theta. Okay? All right, next step. How did we get to here? Well, all we did was divide both sides by theta. Is that a legal move? Yeah, totally. Theta is a number. Is it a positive number? Absolutely. So we don't have to worry about changing the direction of the inequality. All right. So far, so good, hopefully. Now take a look at our picture to the right. If we let the tangent lines A and B, the tangent lines at A and B, so we're taking the tangent to the circle at A and a tangent to the circle at B, they're going to meet somewhere. They're going to meet at that point E. You can see from that picture that the circumference of the circle, right, the distance around the circle, is definitely smaller than the length of all of the reds, right, the polygon, the perimeter of the polygon. So that tells us that AB has to be less than AE plus EB. If we know the circumference, right, this distance around the entire black line, the circle, is less than the distance around all the red lines, then if you take 2 points, we know that going on the arc is shorter than going along here, right? And then along there. So that's all that's saying is BE plus EA, or if you write it as AE plus EB, same two things, that has to be bigger than AB. Next, is your head starting to hurt yet? Okay. We know that theta is equal to that AB arc length, which we now know is less than AE plus EB from this picture. But if we come back to our original picture, we know that AE and EB is the same thing as AE plus ED. Right? All we did was we swapped out EB for ED. How the heck do we know that? Well, again, it's from some other trick. This triangle going on here is what gets us that. All right. Now we move on to what is AE plus ED equal to. AE plus ED is equal to all of this stuff, and you go, where the heck does that come from? Well, again, go back to your theta and your SOHCAHTOA, and you know that tangent of theta is opposite over adjacent. So tangent of theta is opposite, which is this whole AD thing, right? So tan theta equals AD opposite over adjacent, which is OA, and then multiply both sides by OA, and that's where you get AD equals this. All right, so this thing is equal to this, right? We saw that AE plus ED is the same thing as AD, and then that's the same thing as OA times tangent, and that is the same thing as tangent, because OA, look, is the other radius, and it's equal to 1, and there you have it. So now we have that theta is less than tangent of theta, right? See, by the transitive, we're going all the way through. Theta equals this, which is less than this stuff, which is less than this stuff, because ED was bigger than BE, right? Because again, it's a right triangle, so we know that piece is bigger than that piece. So by substitution, this is still bigger than that, because basically we just know that this thing right here, ED, is bigger than EB. And then this stuff is actually equal to this stuff, which is equal to this stuff. So by transitive, we've got theta is less than tan theta. And then by substitution, theta is less than sine over cosine, because that's what tangent is. Again, we can kind of move some stuff around. Multiply both sides by cosine. So you have cosine theta over here, and that goes away. And then divide both sides by theta. And that's where you get this, cosine theta less than sine theta over theta, which is less than 1, right? From there, we already know that sine theta over theta is less than 1, and now we have that it's greater than cosine of theta. So now we've squeezed it in between two things, and we can use the squeeze theorem. We know that if we take the limit as theta goes to 0 of 1, it's just going to equal 1. We also know that the limit as theta goes to 0 of cosine of theta equals 1, because, you know, the limit as theta goes to 0 of cosine theta, what do we always do when we take a limit? The first thing we try is we just plug the number in. So if we just let theta equal 0, what's cosine of 0? It's 1. So as theta goes to 0, the left-hand side equals 1, the right-hand side equals 1, and sine theta over theta is squeezed in between them. So we now know by the squeeze theorem that this right-hand limit, as theta goes to 0 from above, has to equal 1. And the reason why we had to do from above is because we told ourselves we were in that first quadrant where everything had to be positive, you know, a positive theta. But because the function sine theta over theta is an even function, which means if you plug a positive theta or a negative theta in, you get the exact same answer. Think of it very simply. Put pi over 2 in there. Pi over 2, sine of pi over 2 is 1, so you get 1 over pi over 2. Now put negative pi over 2 in there. You get negative 1 over negative pi over 2. The negatives cancel, and you get the exact same answer of 1 over pi over 2, right? All right, so it's an even function, and because it's an even function, the left-hand limit must be the same as the right-hand limit. So now we have the limit as theta goes to 0 from the left is going to be the same thing So the limit as theta just goes to 0 has to equal that. And ta-da! We have finally proven this. We can deduce the value of the remaining limit as follows, right? So we now have the limit as theta goes to 0 of cosine of theta minus 1 over theta. That was the fourth piece that we didn't know from our previous big long thing. We can do some trig work, right? We multiply top and bottom by the conjugate, so then we get cosine squared minus 1. The reason why we do that is because now we can introduce sine squared. Cosine squared minus 1 is the same thing as negative sine squared. The bottom, we're just leaving it as a product for now. Pull that negative sign, that negative sign, S-I-G-N, right? The negative piece out, not sine, S-I-N. Pull the negative out, and then break this apart. Sine times sine, and then we can also break apart the a's and b's in the bottom, the theta and this other piece. Well, we already know what this is from before. It's a 1, right? Because we're now taking the limit of this times the limit of this piece. So we get the negative 1 here times whatever this is. As theta goes to 0, again, try it, right? We always want to just plug in 0. Sine of 0 is, who remembers this, right? 0. Cosine of 0 is 1, and we get 0 over 1 plus 1, 0 over 2, which is 0. 0 times this is 0, and ta-da! We finally have the second piece, or really the fourth piece, is 0. So now we know this other thing. We know that sine theta over theta equals 1, but cosine theta minus 1 over theta equals 0. If we put all of those things together, and remember the original one that we were trying to figure out was these four pieces, and we figured out the first one was easy, it was sine, right? This one was easy, it was just cosine. This one we just figured out was 1. And then this one we just figured out was 0. So we have sine x times 0 plus cosine x times 1, and lo and behold, the answer is cosine x. And probably by this point you can't even remember what the hell we were doing. What were we trying to solve? Well, if you don't remember, our original function, our f of x, was sine of x, and we just found the derivative. So we just proven that the derivative of sine is cosine, something that we thought from that graph, and now we know for sure. The derivative of sine is cosine. That's the first, let's say, rule for trig derivatives that you need to know. Derivative of sine is cosine. So what do you think the derivative of cosine is? Well, here's an example dealing with taking the derivative of sine, right? We just know that whenever we take the derivative of sine as cosine, you can walk through this. This is easy. As I said before, what's the derivative of cosine? Well, strangely enough and nicely enough, it's just negative sine. So the derivative of sine is cosine, the derivative of cosine is negative sine. That makes our life really easy because now we can figure out what all the other trig functions are, because the derivative of tangent is just the derivative of sine over cosine, and we can use the quotient rule. Do the quotient rule with some algebra, and lo and behold, we get secant squared. So now we know the derivative of tangent is secant squared. We can do the same thing with all the other trig functions, i.e. write them in terms of sines and cosines, because we now know what those two are. And we can get all 6 trig functions. Okay, so this is something you're going to want to commit to memory, these 6, because you're going to use them over and over and over again. And the reason why is because trig functions come up all the time. There are a lot of real-world phenomenon that are modeled by trig functions. So that's why you really want to make sure you understand these things. Here's a perfect example. You've got an object, a weight, that's on a spring that's being suspended, from a horizontal surface. So think about a board or the ceiling or something. You've got a weight on a spring. The object at the end of the vertical spring is stretched 4 centimeters beyond its resting point. So if you think about it, if you're not touching the thing at all, the weight just sits at a certain place. Now you're going to pull it down by 4 centimeters and then let go at time equals 0. And this thing's obviously going to bounce up and down, up and down, up and down. Well, the position of that weight at any time t can be modeled very simply as 4 cosine t. And from that, we can very easily find the velocity and acceleration because we know velocity is the first derivative of position and acceleration is the first derivative of velocity, which of course is just the second derivative of position. So here we go. Right? Velocity is the derivative of s with respect to t, right? The derivative of position with respect to time. Or d dt of that function, pull out the 4, take the derivative of cosine, and we know the derivative of cosine is minus sine, and we get velocity as negative 4 sine t. Acceleration is the derivative of that function. Again, we take out the negative 4, take the derivative of what's left over, the derivative of sine is cosine, and we get acceleration as negative 4 cosine t. Now, the object is going to oscillate from the lowest point when s equals 4 centimeters to the highest point s equals negative 4 centimeters. Just a point of clarification. The distance is measured in the positive direction being pulled down. It's a little counterintuitive. So the highest point of negative 4 centimeters just means it's 4 centimeters above its resting point. And the period of this oscillation is going to be 2 pi because that's the period of cosine. There are our three functions: position, velocity, acceleration. There they are graphed all on one graph. You can see that the speed, right, is just 4 times the absolute value of sine t, because the speed was negative 4, right? So that absolute value helps. And it's greatest when sine t equals 1, and that happens when cosine of t equals 0. And you're thinking, how the heck do you know all that? Well, when does sine equal 1? Sine equals 1 at pi over 2. At pi over 2, what does cosine equal? Cosine equals 0. So the object moves fastest as it passes through the equilibrium position s equals 0. Its speed is 0 when sine t equals 0. That is at the high and low points, where cosine t equals 1 and s equals 4. You can follow all these from the graph. At time equals 0, your position, right, you've pulled it down 4 centimeters, then you let it go. And it starts to go back up towards its equilibrium, then it goes past the equilibrium to its maximum height, then starts coming back down towards the equilibrium, goes past the equilibrium, now it's down below it, and it just keeps doing that. Well, as it's doing that, its velocity, right, that's the blue, starts at 0, then you let it go, and because it's coming down, right, negative velocity, it's speeding up till it gets to here, and then it changes direction, or it's getting less because it's slowing down as it gets to the other side. Think about it. It speeds up and then it slows down to the other side until it stops, and then it snaps back in the other direction, right? So its velocity is increasing to the equilibrium point, and then it starts slowing down until it gets to the other maximum point, and then it's going in the other direction. So now it's starting to increase in the other direction to its maximum point, and then slowing back down, right? So that's velocity. And then acceleration also makes sense as you look at it in terms of these things. The instant you let go, it's accelerating, but it's accelerating less and less until when it's kind of, it's slowing down is when acceleration is 0, and now it's accelerating in the other direction. So all those things are kind of intuitive. You can follow through with the idea of what does t equal when all this stuff happens, what does s equal when all this stuff happens, to see how it works. But the bottom line is, this is just an example of a trig function modeling something in the real world. So if you're going to go on to physics, you're going to deal with weights on springs all the time. All right, guys, so most important thing, this stuff. Make sure you know those 6.